Well, depending on how you combine the building blocks, and the building blocks are the PI controller, the anticipation, and the first order filter, you either obtain a series PID implementation or a parallel PID interpretation. Well, in the series PID interpretation, the PI controller is working on the error or the anticipation or the estimation of the error in the future. So both the proportional and the integral part on working on E hat. This estimation of the error in the future is constructed as follows, and you can see here that the first order filter is at the back. It's not only acting on this term over here. Notice also that the names of the parameters have been chosen KCS, TIS and TDS, and the S stands for series implementation. This is because, well, the meaning of those parameters is different if you're using a series PID and a parallel PID. We'll come back to that later. So you can kind of see from what you see over here that the implementation of the series form of the PID controller is as follows. Okay, so you can see this as a PI controller, and this is a lead lag. This is why this series form is used very often in the frequency domain. For instance, when you're doing loop shaping, you can use this lead lag to give you a phase lead in some frequency ranges, and this can be interesting during the design or the tuning of the PID controller. In the parallel PID interpretation, the building blocks, so the PI controller, the anticipation and the first order filter, are combined differently. You can see here that in the PI controller, this block over here, well, the proportional action is acting on E hat, so the estimation of the error in the future, whereas the integral action is acting on the standard control error SP minus PV. You can also see here that the first order filter is only acting in this branch over here. So you can see here that there are three branches: proportional, derivative, and integral. So you can redraw this control interpretation as follows. Well, you can now clearly see why we call this a parallel PID. You can see that the proportional, derivative, and integral action are in parallel, and they simply add up, and then these actions are added and multiplied by the gain of the controller. Okay, this parallel PID algorithm comes with an equation that is this one over here. So there are, well, three main parameters: KC, TI, and TD, but in the background there is also this filter for the derivative action. This is the ISA implementation form, International Society of Automation, and this is also the implementation that you will encounter in most PLCs. Well, the parallel form of the PID controller as the following implementation in the Laplace domain, and the series form as this implementation in the Laplace domain. The parallel form is also called the ideal form, and this is because the three actions act in parallel, and then you have a scaling with the controller gain. This is the most general form, and this means that, well, every PID controller in the series family can be represented by a parallel PID controller, but there are some parallel PID controllers, so corresponding to some parameter sets over here, that cannot be represented by a PID controller in the series Well, this parallel PID controller has a very good interpretation in the time domain. So this is why people in industry like this interpretation or this implementation of the PID controller. The series form of the PID controller is also called the interacting form, and it's less suited for trial and error tuning because the three actions interact, as you can see in the equation. Okay, so the advantage of this form is that it can be used very well in the frequency domain, right? So it's ideally suited for loop shaping. This is what you've seen in last year's course, Fundamentals of Control Theory. So loop shaping is PID tuning, but in the frequency domain. In this slide, we look at the link between the series and parallel implementations of the PID controller, and to find this link, we'll neglect the filtering in the derivative action. This does not mean, of course, that you can forget it in the implementation. No, it is very crucial. But in order to link parameters in the series implementation and parameters in the parallel implementation, well, we have to make this assumption, otherwise the formula would become too difficult. So if we do this, or if you make this assumption that we neglect the filtering in the derivative action, this is what you obtained for the parallel form, and this is what you obtained for the series form. Notice that if there is no derivative action in the parallel form, then this one will disappear. If there is no derivative action in the series form, then this one will disappear. You see that both the resulting parallel form and the resulting series form are identical. So if you're working with a PI controller, well, basically you will see no difference if you're working with a series implementation or a parallel implementation. Well, what we'll do now is write the series form under a parallel form, so we'll have a link between, well, the parameters in the series form and the parameters in the parallel form. Remember that in the other direction it will not always work. So this series form can be written as MV is equal to KCS, and then we have, well, TDS times S, right, plus TDS over TIS. The S over here will cancel out. We have a 1 over here, and then plus 1 over TIS times S. Okay, so this one we can put it under the same denominator, so we have KCS TDS times S plus TDS plus TIS over TIS plus 1 over TIS S. So this one we can take it out. So we'll have KCS times TDS plus TIS over TIS. So we'll have a 1 over here coming from this one, and then since we have taken this one out, we must multiply by the inverse of this one, and we'll have 1 over TDS plus TIS. So that will be the integral action, and we'll have over here, since we have to multiply by the inverse of this one, we'll have TIS TDS over TdS plus TIS times S. So now we've rewritten it in the form that you see over here, so a parallel form, and you can kind of see that, well, Kc takes this form, Ti takes this form, and Td takes this form. When this assumption is valid, okay, so TIS is much larger than TdS, and this is generally the case for good design, because there is a rule of thumb that says that Td over Ti is in general smaller than 0.25. Okay, so this is a rule of thumb. Well, if this assumption is valid, you can kind of see that the parameters for the parallel form and the series form can correspond. So you can use, for instance, parameters coming from a series form and use it for a parallel form and vice versa. Well, if you want to compute things exactly, these are the formulas that you should use. Well, in conclusion, you can see that the equations of the parallel and series PID are different. The interpretation of the parameters is therefore also different, although we have seen that the differences are small if this ratio is small over here, which is often the case for good design. We have seen that the parallel form is more general, right? The implementation is supplier dependent, right? And among all the possible variants, you have, well, proportional action on PV, derivative action on minus PV, right? And this we have seen in the example of the PID controller in the, well, Siemens PCS7 system. So you should always inform about the implemented algorithm before you start optimization. And we have seen, and this is important as well, for a PI controller it doesn't matter if you're working with the parallel and series form because they are identical. Well, remember that we have considered the open loop step response of the PI controller and the open loop step response of the proportional derivative controller. So what you can do, of course, is combine both to obtain the open loop step response of the PID controller. And it's important to understand what you see here on the screen, because if you have a process with delay, what you will have exactly this response of MV until, well, if this is the process delay, until the process starts to react, right? So in the first part of the closed loop step response, until the process reacts, this is the evolution of MV that you will see. And when the process starts to react, so in this region over here, well, then you will see something, you will see a deviation from what you see here on the screen. But in this time region from 0 to theta, where 0 is now the time of the set point change, this is exactly the evolution of MV that you will see. Well, what you see here in magenta is the evolution of MV for the proportional plus integral action plus derivative action. So the following analysis you can only understand if you understand the open loop step response of the PI controller and that of the proportional derivative controller. But of course here what you have is derivative action on top of the proportional integral action. As you can see here, you have the derivative kick, right? And then the derivative action is maintained for a while, but after a while the derivative action is disappearing, right? So for a large t, what you have is only the effect of the proportional integral part, right? Because the derivative part is vanishing. And of course, proportional integral is the integral part on top of the proportional part, here shown in red, right? You integrate something that is constant, so on top of this proportional part you have something that is increasing linearly. Of course, now we can have a look at the influence of the parameters. The controller gain is going to affect this proportional part, but also the rest, right? So if you multiply the gain of the controller, this is going to be stretched, right? And let us have a look at the integral part, right? If the integral time constant is increased, well, the slope will decrease, right? And the integral time constant, well, that's the time that is needed for the integral action to have an effect that is exactly the same as that of the proportional action, as you can see. And of course, in this derivative action, you can influence the derivative kick, as we have seen, and then it's the ratio TD, the derivative time constant, over TFD. This is the time constant of the first order filter that filters the derivative action, and it's this ratio that is kind of imposing the height of the derivative kick. Of course, the whole thing is multiplied by the gain over the controller, right? And this derivative action is maintained for a while, and you can influence this duration by playing with the time constant of the filter that filters the derivative action. As you can see, if you take a larger TFD, well, this derivative action will be maintained for a longer time. And then here you have the influence of all the parameters. Again, it's very important that you understand this, because if you tune a PID controller, for instance, for a process with delay, the first part of the evolution of MV is exactly what you'll see here on the screen, right? And then after the delay, well, MV is going to deviate from what you see. But if you want to influence the evolution of MV, you have to understand the influence of all the parameters on this evolution. Well, as you can see, and this is something that we have seen before, you can use a deadband, right, to prevent that small changes in the error due to noise. If the control error is SP minus PV, so if PV is subjected to noise, well, there will be small variations, but high frequency variations of the control error, and you don't want them to affect MV. So what you can then use is a deadband, and this is a nonlinearity that we have considered in the section on process behavior. So this deadband will be located in the controller just after the computation of the control error, right? And what the PID algorithm will see is the error after the deadband, right? So the error will have to leave the deadband before, well, the error is different from 0, right? And before, well, there will be a change in the controller output. And of course, this is meant to prevent these noisy PV to have an influence on MV, and this will mitigate the effects of noise on actuator wear. Well, let us look at an example in Simulink. Here we have a process, first order with delay, that is subjected to noise, and here we have a PID controller. We have tuned it as a PI controller, and you can set the deadband, and if you go and look underneath the mask, this is what you see. So here you have the error and here the deadband, so this is what the controller is seeing. If we now look at the step response, this is what you see. So here in blue MV, SP and PV, and here you see the error, standard error in brown, and the error after the deadband in green, and here you see the deadband. So you can see here that in steady state, well, the error is in brown here, subjected to noise, but the error after deadband, right, is less subjected to noise, and this is why here you see the influence on MV of this noise much less, right? Of course, the price to pay is that PV is not going to set point. If we now look at a situation where we simulate without deadband, this is what you obtained. Now there is no difference between the error before and after the deadband, so the controller is going to react on the noise, and this is what you see here on MV, and this high frequency noise on MV is going to cause actuator wear. The alternative is of course filtering, but as you know, filtering is going to cause a phase shift in the signal, so it's kind of a trade-off what you will do, filtering or use a deadband, and it will depend on the type of application. Well, have a look at the following site if you want to have an explanation of proportional, integral and derivative control in another fashion using simple analogies. Well, let us now have a look at the adjustment of the PID action. Remember that we have already looked at the tuning of a PI controller. First thing that you have to say is that, well, derivative action has to be used only when necessary. For instance, for a first order system, then a PI controller is sufficient, right? So use derivative action for a slow, between quotes, process when you have a significant second order time constant, right? So what you could do is look at the step response, approximate it by a second order system with delay, and then you'll have the main time constant and the secondary time constant, right? First thing that you have to do is optimize a PI controller, and well, remember that for a PI controller what you will choose is TI, the integral time constant, in the neighborhood of the first or main time constant. I'll call it TP1. Well, then the derivative action is gradually introduced. You can start from 0, but probably that the derivative time constant will be in the neighborhood of this secondary time constant, right? If you introduce this derivative action, you will see that it has a stabilizing effect. The stability margins will be improved, and what you will be able to do most probably is to increase the controller gain a little bit so that you have a faster response. It goes without saying that you have to use a filtered derivative, as we have discussed before, and well, in general the ratio TD over TI should be less than 0.25. Well, in this course we talk about the adjustment of the PID action, and next we'll talk about discontinuation of method 1, so the successive tuning of first proportional action, integral action, then derivative action, and then proportional action again. But of course it could happen that things go wrong, right, when you tune, and that you see an oscillation appearing, and in the worst case this oscillation could even be growing, that you go towards instability, and then you have to know how to react. Well, everything starts with a good organization when you start the optimization. As I've said before, you should look at all curves, right? Set point, PV, MV, and also the disturbances. So prepare these trends. You're going to start probably from a between quote normal production situation where PV is on set point or close to set point. So before optimization, what you should do is write down on a bit of paper the gain of the controller, the integral time constant, and the derivative time constant. And also, well, you're working around a certain working point, and well, this corresponds to a certain MV and a certain PV. So write down the MV that you have at that particular moment, right? And then, and only then, you can start the optimization, right? Well, what happens in case of trouble? You see this oscillation appearing, it is growing, and you want to return, of course, to the initial situation, and you have to do this as soon as possible. So you have to react, but you have to react fast. And this is how you should react. You have to put the controller in manual mode and quickly return to the MV that you had before the optimization exercise. This is this steady state MV that made sure that PV was on set point, right? And then while waiting, you can return to the initial control settings. And after settling, this is important, when PV has returned to its value that you had before optimization, you can return to automatic mode. So you can see that when you start adjusting a PID control loop, you have to take some precautions and you have to be ready to deal with potential problems. Well, we can now look at the adjustment of the PID action, right? For the case of a second order system with delay, two time constants. The main time constant is 5 seconds, the secondary time constant is 2 seconds, and well, the delay is 3 seconds. And what we'll do is first tune a PI controller using this method 1, and then we'll adjust the derivative action, right? Here we work with B is equal to 1. So remember that you have to tune a proportional controller first. It is not said here, but this is for tracking, right? You can test with a few controller gains and then we'll take the one that is appropriate for you in terms of speed of response and overshoot. And here we have kept this one. We know that the main time constant is 5 seconds, so now we can tune the integral time constant, right? And we start from 5 seconds as this is the main time constant of the system, and we can test for values of TI that are in the neighborhood of this 5 seconds, right? And here we keep these values. Well, we gradually introduce the derivative action, and as you can see, while we do this, we slightly increase the gain. This is because this derivative action will be having a stabilizing effect. The stability margins will improve, so you can increase the gain a little bit to have a faster response, to have a better speed of response. And if we look here, we retain the values corresponding to, well, TI is equal to 5 and TD is equal to 2 seconds. It's always a good idea, if you have a second order type system with a delay that is not too large with respect to the main time constant, to take an integral time constant in the neighborhood of the main time constant and a derivative time constant, the derivative time, well, in the neighborhood of the secondary time constant of the system, right? And here we have added the, well, response of MV, and you can see here that with alpha is equal to 0.1 we have a day kick that brings us in saturation. And this is why you should always, when you tune, right, look also at MV. And here probably you would have a better response if you would take a value of alpha that is a little bit larger. So in this subsection of the PID controller, we consider integrator wind up, and we look at mechanisms that can allow you to implement a discrete time PID controller without integrator wind-up. First, some words about wind-up, integrator wind-up or reset wind-up. This mechanism occurs when the controller output, MV, has no effect on the process variable PV because the feedback loop is broken. We'll consider three situations. The first one is output tracking. We've considered this before. We'll consider also manual mode, and we'll consider limitations of MV. Right? So the problem is that the feedback mechanism is broken. MV has no influence on PV. Well, the integrator term sees an error that is either positive or negative, so this integral term winds up. Depending on the sign of the error, the output increases or decreases without effect. This is the wind-up mechanism. Then, when the feedback loop is active again, well, it takes a long period of dewinding before the situation normalizes. Well, integrator wind-up can lead to major upsets in production, and the complexity of the mechanism that you have to implement in order to prevent wind-up issues can easily become very complex. We have already seen, for instance, well, the implementation of the interlocks in a cascade. But of course, you cannot ignore this mechanism because not implementing it can have very severe consequences on production. Now that we understand the wind-up mechanism, we can look at situations where this wind-up is occurring. For instance, it is occurring when the process is driven in a limiting condition, right? For instance, actuator limits maximum heat transfer. It can occur during a temporary disruption of production in the paper industry, for instance, a paper break, or it could come from a failing measurement device. And of course, we have seen that if you do not take any precautions, you can expect wind-up in cascade control structures. You will also see wind-up if the interlocks are not properly implemented during startup, shutdown of the process, or when switching between modes of operation. For instance, in the paper industry, when there is a grade change in the paper process, the grammage controller is often bypassed, and then you have to, well, do the interlock strategy, implement the interlock strategy in a proper fashion. Well, let us look at a simulation that is illustrating this integrator wind-up mechanism, and in this case we work with a first order system, right? And you can see here that, well, the input of this first order system is limited in between 0 and 100%. So it could be, for instance, that the actuator is a control valve that will close at 0% and be fully open at 100%. And of course, if you try to impose an opening of 200%, well, this valve can and will not react to that, so it will stay open at this full opening of 100%. So what we'll do is compare two controllers. The first controller, and this is with the light colors here, so here you have MV, here you have PV. This is a PI controller where the limitations of MV have been implemented correctly, as will be shown later on in the course, right? And this second closed loop response with the darker colors, dark green and dark blue here, very dark blue, well, this is a closed loop response with a PI controller where there is no limitation of MV whatsoever. right? So let us have a look and compare the two responses. Well, first we do a set point change that is such that you do not run in the limitations, right? So, well, then obviously, well, the response of the two PI controllers is identical. Here at this time we do a set point change that is such that you run into the limitations, right? Here is the response of the correctly implemented controller. It limits MV to 100 and it makes sure that there is no wind up of the integral action, right? And this other controller, well, imposes a proportional kick that goes above the limitation, but in practice, of course, this limitation, well, is physically present on the physical process, so the valve will not open more than 100%, and this is why the two responses are of course identical. So when you look at the response over here, you do not see anything happening, right? But you can see here on the response of MV that indeed there is a problem that is occurring, because for the controller that is not implemented correctly, well, it will see an error, right? And well, it will start to integrate this error, right? But of course MV is limited, and what you see here is actually the open loop response of the system. It will evolve to a value of PV that is 100, since the gain of the process is 0.5. We have 100 here, so we'll have 50 over here, and this time constant, well, this is the time constant that we see over here, right? But the indication of wind up, you see it over here. And of course you will start to see the influence of this wind up on the process as soon as you make a set point change in the other direction, right? Because, well, in the case of the PI control that is correctly implemented, the proportional kick, right, will impose a change on PV directly, and very quickly you'll have PV on set point, right? Whereas with the badly implemented PI controller, the proportional kick is going in the right direction, right? But this is still far above 100, right? So you will not see any change on the actual process. It will still run the process with a fully open MV. And then of course it will see in this region here a negative error, and you will have this period of dewinding. And the process will start to react only when, after this period of dewinding, well, you have an MV that is now, well, lower than 100%, and this is when the process is starting to react. But you do not have any proportional kick over here, so you'll have to count on the integral action, right, to make sure that PV goes on set point. So this is kind of a motivating example to implement mechanisms that go against integrator wind up, and this is what we'll do next. Well, if you take a controller from a library, from a vendor, you will see that it has an integrated anti-wind up mechanism, for instance for interlocks, for manual mode, and for saturation. If you have to implement your own PID controller, you will have to implement this anti-wind up mechanism yourself. And this is what we'll do next. You will find in the literature quite a lot of anti-wind up mechanisms with very subtle differences. We'll consider two of them in this course, and a third mechanism is given for your information only. So we'll start with integrator reset, right, and then we'll have a look again at this positive feedback implementation that has an automatic anti-wind up mechanism. So for simplicity, what we'll do in the next few slides is not considered derivative action in the anti-wind-up mechanisms, but of course it can very easily be integrated and the same IDs apply. What you see over here is the PI controller using the Euler backward difference approximation. The derivative action is left out, and what we want to do is add output tracking. So a first naive idea is to implement it as follows. Well, the equation implementing output tracking is put just after the PI algorithm, and you can see that indeed if, well, track on, this binary signal goes to 1, then indeed MV will be equal to the value that you want to track val. But you can see that there will be a problem because you'll have wind up of the integral action. If you have your controller in output tracking mode, then the feedback mechanism is broken and MV has no influence. Well, this MV that is produced over here has no influence anymore on PV. If the controller sees an error, well, if this error is positive, this one will wind up to a very large value, and if it is negative, it will wind up to a very large but negative number. So this is called wind up, and this is explaining why clearly this is a naive idea and this is not the way to go. The correct implementation of the PI algorithm with output tracking is to use integrator reset. So the equation is written over here. If track on, the binary signal goes to 1, then you reset the integrator value to a value that is track value, the one you want to follow, minus the proportional value. At the next equation, what you do is that you add this proportional value. So you see here that if track on goes to 1, MV will be indeed equal to the tracking value, but you have the advantage that there is no wind up of the integrator or the output of the integrator. On the contrary, well, this integrator is ready and is put at the correct value if at the next sample instant this one goes to 0. Well, this value is set to an appropriate value. Well, in reality, you'll have to combine this with derivative action. So you'll have an equation here that will produce the derivative action, right? So you will have to add the derivative action, and you'll have to add also the MV feed forward that we have discussed previously. So in order for this to function, you can clearly see that, well, if you have output tracking, so if this signal goes to 1, then the integrator has to be reset to this value you want to track, minus this one, minus this one, minus this one. So minus MV D of K and minus MV feed forward. So this is the way to adapt the code if you're adding a derivative action and if you're adding feed forward. Remember that the feed forward has to be then an input of your PID controller block. In the PI algorithm, you'll also have to implement a manual mode in such a way that there is no wind up, and the way to go is to do this as follows. So the IDs are exactly the same. If you're in manual mode, then the output of the integrator has to be reset to a value that is the value of the output in manual mode minus the proportional part. Of course, you can also do a similar kind of implementation for a PID algorithm, so that you have derivative action and where you have a feed forward. So you can see here that output tracking, manual mode, and also limitation of MV are treated separately. Of course, you have to integrate the three aspects: output tracking, manual mode, and limitation of MV in the PID controller implementation. Well, the last thing that you have to do is to implement actuator saturation or actuator limitation in such a way that there is no wind up of the integral action. And the way to do it is as follows. Well, if the output, okay, so the sum here of proportional and integral goes above the maximum value, then you have to reset the integrator to the maximum value minus the proportional value in such a way. Well, you will have an MV here that will be MV max, and there is something similar, of course, if, well, this part, the proportional part plus the integral part, goes below the MV min value. So this is the implementation for a PI controller, but as I've shown you in the case of output tracking, you can also implement this, and you should do it, for the case of a PID controller and when there is feed forward. Well, we have already used this positive feedback implementation of the PI controller to introduce limits on MV, saturation limits, but also limits on the rate of change of MV. You can also very easily integrate output tracking, and similarly you could add a manual mode. So instead of track on, you have then, for instance, manual, right, Boolean signal, and you have here MV manual, right, but the IDs are exactly the same. As you will see, you can even combine with, for instance, feed forward. Indeed, we'll start again from this positive implementation of the PI control that we've seen before, and we'll add the feed forward. The aim is to limit, of course, the sum feedback and feed forward. Well, this is difficult when everything is implemented like so. So what we'll do is redraw this control scheme a bit differently, and we'll do it like this, right? So we add the feed forward in front, but if you add it in front, of course, it will also influence this branch over here, and it should not. So you add it over here and you subtract it over here, and this implementation and this one are completely equivalent, but of course this one is suited to add output tracking and actuator limitation, and this actuator limitation comes again in the form of saturation and rate limitation, so a limitation on the slope of MV, and you could of course add manual mode. This slide is for your information only. We have seen in the subsection devoted to override control that instead of selecting the error, so here E1, E2 or E3, using min-max selectors, what you could do is use several controllers, here 3 PI controllers with different tuning parameters, and select the appropriate MV, here MV1, MV2 or MV3, according to the constraint. Of course, only one of the controllers is active between quotes, and the other two controllers are tracking the active controller. The tracking strategy can be implemented as follows, using this positive feedback implementation of the PI controller. And as you can see, the selected MV is fed back to all 3 controllers through a first order system that has time constant, well, the integral time constant of the corresponding PI controller. In this subsection we come back to IMC PID tuning, but in the general case we had already considered IMC tuning, but for 4 types of processes. Here we consider many more processes, and for these processes, well, sometimes, well, tuning rules are given for PID controllers, whereas before we had only considered PI controllers. Note that this table, this IMC tuning table, has been drawn from the following source, and as you can see there are many more processes than the processes that we had considered before. We have, well, here for each line a process with corresponding proportional integral or proportional integral derivative tuning rules, right? If you don't see anything for the derivative time constant, it means that a PI controller has to be used, and for instance this is the case, as we know, for a first order system, right? For other systems, for instance first order with delay, you have tuning rules that lead to a PI algorithm or to a PID algorithm. The notations are of course slightly different than the ones that we had considered. Here tau c is what we have called TCLP, the designed closed loop time constant, the, well, design parameter, right, or the tuning parameter. Well, the gain of the process is K, right, and we have called it KP, right? And you can see here that time constants are with a tau, whereas we have used a T and the time constant of the process. So for instance, for this particular case, right, first order system with delay, if you go to the PI controller, you can see that you should use an integral time constant that is time constant of the process, and that the gain of the controller is this quantity, but you have to divide by the gain of the process, right? So in this column what you have is the loop gain, static loop gain, Kp times Kc, right? So you have to take this value and divide by the gain of the process to obtain the gain of the controller. And of course, if you take this line over here, well, the procedure is exactly the same, but you'll have now also a derivative time constant, so this will lead to a PID controller. Well, this is the procedure to use this IMC-based PID table. Through first principle modeling or through experimentation and, well, identification using graphical methods, you have identified the process and obtained the corresponding process parameters, and this leads to a process that is identified by a, between quotes, case in the IMC-based PID table, right? Then you have to set the desired closed loop time constant, right? In the table that's tau c. Previously we have said it's called TCLP. Once you have this desired closed loop time constant and you have selected the appropriate line, well, you have access to, well, the integral time constant and the derivative time constant. You just have to take the corresponding expressions, right, and replace the values of the process parameters by the process parameters that you have identified, and replace TCLP by your design parameter. For the first column, right, this is giving you the static loop gain, so you have to obtain the controller gain by taking this expression in the first column and divide by Kp. In some cases, whoa, this IMC tuning will lead to a PI controller, and in some other cases this will lead to a PID controller. Well, in this slide we talk about the origin of the table that you have seen. Well, the authors of the original article on IMC PID tuning have proceeded as follows to obtain the IMC-based tuning table. They have considered different process structures, the process structures corresponding to the cases in the table, and for each of these process structures they have designed an internal model controller or IMC controller imposing a closed loop time constant TCLP or tau c. Right? We will look at this internal model controller strategy at the end of this course. From the IMC controller, they have constructed the equivalent series feedback controller, and they have approximated this controller using PID type approximations, right? You remember that E exponential of minus theta s is approximately 1 minus theta s, right? Well, this type of approximations they have used to obtain an approximation that looks like a PI or a PID type controller, thereby obtaining the table that you have found in the course, right? We will follow this procedure for a first order system with delay in the last section of the course, so that you can understand, well, the origin of this table better. Well, IMC tuning leads to responses that are smooth without cycling and overshoot. Notice that very often there is a hidden underlying assumption, that is that theta is small with respect to the main time constant, and this is coming from this PID type approximation that is often used in the background, which says that exponential of minus theta s is 1 minus theta s, and this is of course only valid for small theta. Remember that sometimes the PID implementation uses a normalized controller gain, and if this is the case in the formula, you should use the normalized process gain KPN. Of course, you also have to set the desired closed loop time constant, right? And often it is set, well, smaller than the main time constant of the process, right? Very often what is done is that the desired closed loop time constant is set as the open loop or the main open loop time constant times a factor gamma, where gamma is in a range 0.2 to 0.9. If you take gamma is equal to 0.2, so the desired closed loop time constant is smaller, this is of course going to lead to more aggressive control. Well, the fact that the closed loop time constant TCLP is the design parameter makes this method easy, for instance, for tuning of cascaded loops, because you know that the, well, closed loop time constant of the inner loop has to be 3 to 5 times smaller than the time constant of the outer loop. Sometimes it is also interesting to know that two separate control loops have exactly the same closed loop time constant. For instance, in a combustion, right, it would be nice that the flow of fuel and the flow of oxygen have exactly the same dynamics, and you can ensure this by using IMC tuning and by setting 2 times the same closed loop time constant. Although this is not really relevant for the process industry, there are IMC tuning rules available for unstable systems. You'll have to look at the literature for this. By construction, the IMC tuning method has been designed for setpoint tracking. If you have a disturbance rejection problem, you'll have to take the PID tuning parameters and increase the controller gain substantially. In this video course, I will skip the section on loop shaping because this is something that you have investigated in other courses, and I will also skip the section on the PI controller and the first order system. I will, however, show you how you can obtain PI tuning parameters for this processor here that you will not find in the IMC table, right? You will see that in a matter of minutes you can obtain the tuning parameters for this PI controller much faster than you would obtain them using loop shaping. Well, let us consider a process described by this transfer function here, and this type of transfer function is typical of thermal processes, and the process parameters, so the gain and the time constant, could for instance have been obtained using an identification package. Well, if you go and look in the IMC tuning table, you will not find this third order system, right? So what we can do is try to approximate it using, for instance, a Broida model. So one time constant and a delay. You could do the same exercise with two time constants and a delay. So what we'll do is use this Skogestad approximation. Here we have three time constants, right? We keep one of these time constants, so we have 10, and well, the two remaining time constants for half of the value will add it to the time constant that we have kept. So 10 plus half of 10 plus half of 10 is 20 seconds, and the remaining half will put it in the delay. And this is how we very easily obtain an approximation using a Broida model, and we can use it to tune a PI controller using the IMC PID tuning method. If we now compare the step responses of the actual process in blue and of the approximation in orange, you can see that indeed we have obtained a very crude approximation of the step response, but still it is good enough to obtain tuning parameters for the PI controller. If you're not satisfied, what you could do, and you could do the exercise, is approximate the process using a delay and two lag time constant, and that type of process is also in the IMC tuning table. If you look at the IMC tuning table line or case G, right, you will see that this corresponds to a Broida system, one time constant 20 seconds here, gain of the system 2, and delay 10 seconds. And this is the line that corresponds to, well, a PI controller, right? And the resulting PI parameters, right, are given over here. And as you can see here, this is the desired closed loop time constant, and what we'll do is simply impose the same closed loop time constant as in open loop, so 20 seconds. So if you go through the formula, you have here a integral time constant of 20 seconds. This makes sense, right? It is equal to the, between quotes, main time constant of the system, and we have a gain here of 1/3. Well, here you see the closed loop response on the actual system. Here you have Setpoint and PV, and as usual you should also have a look at the, well, manipulated value, right? And you can see here that in a matter of minutes we have obtained PI tuning parameters for a PI controller acting on a process that is considered to be rather difficult to control, because we have, well, 3 times the same lag time constant, and this is kind of inducing an apparent dead time. Well, let us look at some symptoms that could be indicative of problems in control loops. Let us first look at performance changes. They could come from process changes, and if they do, well, the changes will probably be slow. The changes might also result from changes in the dynamics, and then the likely source is, well, adjacent loops that create upsets, right? And of course the problem could come from, well, sensors, problems with sensors, or problems with actuators. If the problem or problems appear and disappear occasionally, well, they could result from a change in working point. If you produce something new, another product, well, you end up in another working point, and it might be that the dynamics are different. For instance, if you have tuned a controller aggressively around a particular working point, and you end up in a working point where the process gain is higher, well, this is going to lead to oscillations. We'll see later in the course how you can deal with this by adapting the controller to the working point using gain scheduling or controller scheduling. Well, if you see constant deviations from the set point, well, first of all, have a look if this controller is in automatic mode, and if it is, well, it could result from insufficient integral action or from a saturated manipulated value. What could also be happening is that this controller is in tracking mode for some reason. Well, problems often take the form of oscillations, and well, you should be able to kind of know all the likely sources of oscillation on PV. We have seen too much integral action, right? Then you will see oscillations between MV and the control error, or PV, that are out of phase, in the neighborhood of 90 degrees out of phase. If it's coming from too much proportional action, you will see oscillations, but they will be in phase or slightly out of phase. You will also see oscillations if you have an integrating process with a controller that has too much integral action. Remember when we had a look on process behavior and, well, second order oscillatory systems, we had seen that if you put two integrator in series and you close the system, you have constructed the perfect oscillator, right? Well, if you have an integrating process and a PI controller with too much integral action, you're very close to this situation. Loop interaction, so coupling, is also going to lead to oscillating behavior on PV. We'll deal with this later on in the course, and we have seen that stiction, a form of nonlinearity, can lead to this special form of oscillation of PV, and it is recognized by this sawtooth oscillation on MV. You can also very easily have oscillation when you have a system with dead time, where the dead time is large with respect to the process value, and you use an aggressive control. We'll deal with that later on in the course when we tackle the Smith predictor. Well, a noisy MV is probably coming from an unfiltered process value that is used for control, or an unfiltered derivative action. It could also be, of course, that the derivative action is filtered, but that the high frequency gain is too high, and this can be noticed by this derivative kick that is too high. You will, of course, also encounter quite a lot of problems in cascade control structures. The first thing that you have to check is the interlock strategy, and this is something that we have discussed when we have discussed cascades. Also, you could have problems with limitations of the secondary controller, so the MV of the secondary controller is limited, right? Or the MV of the primary controller is limited, and this is equivalent to having the set point of the secondary controller limited. And if you do not tackle these problems, this will lead to wind up. Well, here we have a nice summary of all the performance criteria that we have considered in this course. So first of all, overshoot expressed in a percentage of the steady state PV, the rise time, the time that you need to go from 10% to 90% of the steady state PV, the settling time, this is the time that you need to be in a plus minus 1% band, so a 2% band around the steady state value, right? Sometimes this settling ratio is used. It's really the rise time over the settling time in percent, and well, it is considered that if this settling ratio is smaller than 25%, then you have tuned your controller too aggressively and that this rise time is too small. We had considered the decay ratio. Remember that we have used this when tuning a controller for disturbance rejection. Then we had the quarter decay ratio. We could tune the controller in such a way that for a set point change, well, the ratio between two peaks was 1/4. And of course here we have the static or steady state error. Well, this is the difference between the set point and the value of PV in steady state. Well, it is often better to look at the performance of a controller in terms of a criterion, which makes it easier to compare different control strategies, and you will see that many packages allow you to compute such costs. Here you see, well, 3 performance criteria for set point tracking, right? And what they do is look at the deviation from set point, and well, here in this formula the time starts to run after the set point change, right? So you have, for instance, different variations. Here, for instance, you have the error squared, right? So high deviations will be penalized more, and here you have the time squared. So high deviations and high settling times are penalized more. Of course, for disturbance rejection, the set point is assumed to be constant, so this dependence on time disappears, and you have then the integral of the absolute error and the integral of the error squared. Well, this is for your information only, but you have seen in the example of the Siemens PCS7 PID block that a whole part of the control scheme was dedicated to set point handling. Well, as you can see, there is a limiting of the set point to a low or high value. There is a rate limitation, and for instance, what you can do is switch on and off this ramp on the set point. Of course, you have to handle also the choice between external and internal set point, right? This is done with this Boolean signal, and there is also a mode that allows you to make sure that the set point follows PV. This is sometimes used to implement some forms of manual mode. If this one goes to 1, well, set point follows PV, so the control error is 0, right? And you cannot have integral wind up. In any case, if you're in external mode, or if SP is tracking PV, you have to make sure that the internal set point is following the active set point, right? If one of these two conditions is 1, well, you have a 1 here, link on is going to 1, and the internal set point is going to follow the actual set point. In this way, what you will do is ensure that when you switch to internal set point, you'll have a value of the internal set point that was the last value of the set point just before switching to this internal mode, and not a set point from a few weeks ago. Well, it's time again for a little quiz. So what you see here is the response of a Broida system. So it's a first order system with time constant 10 seconds, delay 10 seconds, and the gain of the process has to be determined. And it is the closed loop system with a PI controller, and here it is. So it's the standard PI controller with B is equal to 1. And the question is, can you identify the process gain, the integral time constants, and the gain of the system? So I will show the question, and as usual, use the pause, rewind and forward buttons to find the solution, and try to do this by yourself first. So these are the correct statements, and here you see the response again. Okay, so it's time for pause. Well, it's quite easy to obtain the gain of the process. You wait until, well, MV and PV have settled out. This is the case over here, and you can see that an MV of 60 corresponds to a PV of 30, so the gain is 0.5, right? And you can clearly see here that the controller gain is 1, because an error at the time of the set point change of 30 results in a variation, a proportional kick of 30 over here. So we have a, well, gain of the system that is 0.5 and a gain of the controller that is 1. So this leaves us alternative B or alternative C, right? So we have now to look at the, well, integral time constant, and you can see here that the proportional kick is 30, right? And you have a delay of 10 seconds, and in this delay of 10 seconds, well, the integral action has added, well, something that is equivalent to the proportional kick, right? And we had seen in this static or step response analysis of the PI controller that the time that is needed for the integral action, right, when there is no reaction of PV, of course, to add something that is equivalent to the proportional kick is, well, the time of the integral time constant. So here you can see that the integral time constant is 10, right? A TI of 100 would cause something that would have a much smaller increase. So the correct answer is C. Well, let us do another one. Here's a question on, well, IMC PID tuning, and you have to tune a PI controller, right, using the IMC tuning method for a Broida system again. So a system with a time constant, a delay. The time constant is 10, the delay is 2, and the gain of the process is 2. And what you want to achieve is a closed loop time constant of 8 seconds. And the question is, how are you going to tune the PI controller, right? So again, we'll go over the question and show you all the alternatives. Here they are. Use the pause, rewind and forward buttons so that you can try to find the answer by yourself. Well, this is an easy one, right? So we have the Broida system, 1 time constant, 1 delay, and we want a PI controller, so we should look at case G over here. So really the integral time constant is the time constant of the system, so that's 10 seconds, right? And we have to take this one over here. So this is tau is 10, tau C is 8 and theta is 2. So this one here will be 1, but you have of course to divide by the gain of the process, right, to obtain the controller gain. So you'll have 1 divided by 2. So this means that you have a controller gain of 0.5, right? And we had said that the integral time constant is 10 seconds. So this is the correct answer. Well, since this is so much fun, let's do another one. Well, here you have to associate the closed loop responses that you see here on the left with the correct PID controller, and you have to know that here the most general ISA, International Society of Automation, PID controller is used. So for instance, here we play with these parameters B and C, B that you see in the proportional error and C that you see in the derivative error. So there are 5 responses. I will go over them slowly, and again you can at the end pause this video and use the rewind and forward buttons to have a look at the solution, but again try to do this by yourself. So you have 5 closed loop responses, and here you have 5 types of PI controllers and PID controllers, and you have to associate them with the corresponding response. Well, this one looks like it is a bit more challenging, right? So let us have a look. We have PID controller, so we should have derivative action, and here clearly you can see this derivative kick. Here it's less visible, but this is also due to derivative action, but this is with C is equal to 0. So you have PV that is changing, and the derivative action will go in the other direction than the proportional kick, right? So this is here a PID controller with C is equal to 0, and so this is for this first one, right? Then we had seen another PID controller with C is equal to 1, so this is corresponding to this one. You can clearly see the derivative kick at the set point change and the derivative kick at the other side when PV is reacting, right? And well, the other 3 responses are therefore responses from a PI controller, and you can see that you have here a proportional kick, here a proportional kick that is 2 times smaller, and here no proportional kick, right? So if we look at what is left, well, you can kind of see that this one corresponds to a B is equal to 1, so this is a standard PI controller where the proportional action is acting on the standard control error set point minus PV. Here we have reduced the proportional kick by 50%, so this corresponds to B is equal to 0.5, and the other one corresponds to a situation where you do not have a proportional kick and you count on the integral action to bring PV on set point.